problem.
Yes, thank you. You motivated my talk very well. So it's the fine-grained counting complexity that I will talk about. And I will start with counting, because most of you are familiar with the fine-grained part. And this is the first part in the series. The second part will be given by Radu, who is probably watching at home. So let us look at the 50 shades of fine-grained. So we have different problems here and reductions between these problems. So a lot of focus has been on polynomial-time algorithms and trying to show that they can't be improved. And the ETH and the strong ETH are hypotheses that can be used in this exact algorithm framework to show that you can't get faster exact algorithms. But ETH also implies that this parameterized class W1 is different from fixed parameter tractability. So using ETH, you can also rule out FPT algorithms. And what I will talk about today is counting. So we will look at yet more hypotheses, namely the counting exponential time hypothesis. This one is implied by the ETH. And Radu tomorrow will talk about the counting W1 classes, so fixed parameter tractable counting problems. So the outline will be to look at the classical case first, so the polynomial time setting, since I'm sure not all of you are familiar with counting complexity. Then we will put on a fine-grained lens, look at some specific problems, and I will mention some open problems. So in the classical era, we were looking at polynomial time algorithms. This looks like ruins, but really it's beautiful structures that we built in the polynomial time world. So classically, we make this distinction between decision and counting as follows. So in the decision world, we look at SAT. Is a CNF formula satisfiable? And NP is in the class of problems L. So let me write them like this. So they're not subsets of words. They're not sets of words. They're just functions that map words to 0, 1. That's equivalent, of course. And NP contains all such problems that reduce to SAT under polynomial time many-one reductions. And in the counting world, we can do something very similar. We can look at number SAT, which is the problem where you're given a CNF formula and you want to know how many satisfying assignments there are. And then we can define a class sharp P, or number P, which is the class of problems where the output is now not just 0, 1, but it's a number of satisfying assignments, for example. And sharp P contains the problems F that reduce to number set. And of course here it's not clear what it means to reduce between counting problems. It's not clear directly what this means. So let me give an example. So if we have this small graph and we want to count all Hamiltonian cycles, there are like 3 of them, then we can reduce this problem to SAT as follows. We can map the graph to a circuit C. It's a Boolean circuit. And its input variables are, since we're looking for a subset of edges here, the input variables will indicate whether the edge is in the subset or not. So we have one Boolean variable for every edge. Then we can construct a circuit efficiently, and it's a polynomial size circuit, so that the circuit accepts if and only if the structure that we see is a valid Hamiltonian cycle. Yeah, so this is very I'm just saying this problem is in NP. I'm saying this in this fancy manner. But note that this reduction preserves exactly the number of solutions. So if we had 3 Hamiltonian cycles here, we will have 3 satisfying assignments down there. And this is the type of reduction that we use to define a number P. So it's a parsimonious reduction. The reduction R is called parsimonious from F to G. So F and G are counting problems. And we want that the number of solutions to the instance x is exactly equal to the number of solutions of the instance R of x. And we want this to hold for all inputs R, x. So this is a parsimonious reduction. And number P is then the class of problems that parsimoniously polynomial time reduce to number set. Or equivalently, we can also look at a machine model here. We can look at the number of non-deterministic runs that lead to an accepting path in a Turing machine. That's the very same thing, if you think about it. But since we're in fine-grained complexity, it seems like we define complexity classes using problems, not machine models. So I chose this route. So, and why is counting interesting? Well, counting is interesting because it's harder than deciding. Right? You can easily find a solution here, but if you want to look at or count all solutions, you sort of need to look at the whole solution space in some sense. And this is made precise in this theorem. Namely, the whole polynomial time hierarchy is contained in P when you have access to a number P oracle, like counting the satisfying assignments, for example. So this means that if we can count solutions to 3 CNF formulas, then we can actually decide quantified Boolean formulas. So quantified Boolean formulas exist for all formulas like this, Boolean formulas. And the star means that we can actually only decide quantified Boolean formulas if the quantifier alternations, the number of them is constant. Because that's pH. If it's unbounded, we would have P space, and this class is contained in P space. So in some sense, this counting P class is sandwiched between finite alternation quantified Boolean formulas and unbounded ones. Yeah, so number P, in particular, number P is much harder than NP. So that's why counting is sort of interesting from a complexity point of view. Let me give you some examples. So we've seen that you could count the number of Hamiltonian cycles, but you could also look at an optimization problem, like compute the size of the largest clique. Formally, that's also a counting problem. And you could look at algebraic problems, like the input could be a matrix, let's say with small integer entries, and you want to compute the value of the determinant of this matrix. That's an algebraic problem. And this problem turns out to be number P complete using the standard NP hardness reduction, which turns out to preserve the number of solutions exactly. On the other hand, a problem such as this, an optimization problem, is not likely to be number P hard, because this problem is actually in P to the NP. You can guess the largest clique, and you have to verify that it is the largest clique. And the determinant is in polynomial time. So they can have different sort of can fall into different classes, these counting problems. So what's the most interesting counting problem, or the one that has been studied first from a complexity point of view? That's counting perfect matchings. Let's look at counting perfect matchings in bipartite graphs. So on the left, we have a bipartite graph, and these are all perfect matchings in this bipartite graph. And let's say there are D plus D vertices, so D on the left, D on the right. Then we can turn this into a matrix, a D times T matrix A. It's not quite the adjacency matrix, but it's some kind of bipartite adjacency matrix where Aij is 1 if and only if Ij is an edge. And then the number of perfect matchings turns out to be exactly equal to the permanent. And the permanent, let me define it for you, is this quantity. So you sum over all permutations. So note that you can look at these perfect matchings as a mapping from the left to the right, like a function. And that function, because it's a matching, has to be bijective. So it has to be, it's a permutation. So that's why summing over permutation here makes sense. And then this predicate, so the product, just checks that the given permutation, the given matching, is actually a matching in the graph. So if we just put 1 here, then we have the number of perfect matchings in the complete bipartite graph. And with this predicate, we count the number of perfect matchings in the graph that we care about. And how can we compute the permanent? Well, one way to do it is to do it naively. So we just take the sum over all permutations, and then this predicate can be computed in polynomial time for each pi. And this takes time d factorial, roughly. So let me disregard polynomial factors. This takes time d factorial. We can actually, like Fedor talked about this yesterday, we can actually often improve d factorial type bounds to something faster. And something that will help is that we can compute this quantity in polynomial time. Because the products and the sums are all bounded, polynomially bounded. So why does this help? Well, if you multiply this out, if you were to multiply this out, of course we don't want to do that because that would be too costly. Then you would take the sum over all functions. Because every I gets mapped to every j, so if you get all combinations, and this means that you sum over all functions and you get all of these monomials here. That's good because the sum contains as a subsum all permutations, but of course we overcount it. So we need to sort of subtract all functions that are not permutations. And such a function turns out to be not a permutation if and only if it's not surjective. Yes. So what do? First we subtract all functions, all monomials corresponding to functions that don't hit a certain index j, and we do this for all indices j. So now we have all functions that don't hit a certain index, but they might also not hit some other vertex. So we are undercounting again here. So I'm just saying we do inclusion exclusion here. So we have to add those functions again where we miss 2 vertices in the output, and so on. So there are just a few steps of these. Well, exponentially many steps. But if you write this out, you get Reiser's inclusion-exclusion formula. And this is a really old formula. So we just sum over all sets S of indices that we want to avoid in the output. And then we have some -1, +1, depending on where we are in this process. And then this product, this sort of polynomial, this product can be computed in polynomial time, and it's exactly this sum of all functions. So what this means is that Reiser's formula gives an algorithm for the permanent that runs in time d times 2 to the d, which is, well, much faster than d factorial. And sort of from a fine-grained perspective, this is great. But why should it be 2 to the d? Why I haven't even said why it should be polynomial time. Why it can't be polynomial time. So let's start with why. Let's argue why it can't be polynomial time. Probably. So and to do that, let us compare the permanent and the determinant. So first, I will say that parsimonious reductions are not sufficient to rule out that the permanent is a polynomial time. And the reason for that is that the permanent is actually easy in some sense because it's so related to the determinant. It's easy because mod 2, these two quantities are equal. Just a minus 1 sign, if you take in mod 2, you get 1, so they're equal. And yeah, many algorithms in fine-grained complexity rely on this sort of connection. Okay, so this means that the permanent cannot be parsimoniously hard, because if there was a parsimonious reduction, then the number of satisfying assignments of the input formula would be equal to the determinant of some output formula mod 2. But we know that distinguishing a formula having one solution from 0 solutions is probably a hard problem. So using the isolation lemma, we would then get that RP is equal to NP. So okay, this type of reduction does not suffice. All I'm saying is we need to move on to different types of reductions. And it's not 100% clear what these types of reductions should be, right? So, in some sense. But we just use the most general kind of reduction, namely the polynomial time oracle reductions. So here the reduction is a Turing machine. It gets an oracle. It gets oracle access to G, and we just want that f of x is computed by this oracle Turing machine when it gets access to the oracle. And under this type of reduction, Valiant actually showed in this classical result that number set reduces to the permanent. So if the permanent is polynomial time, then the polynomial time hierarchy collapses. So we don't believe this is true. But I said the permanent can be computed in 2 to the d. And in terms of fine-grained, we want to know, can we do it faster at all? In order to get there, we need to sort of review the proof that the permanent is hard. And I will actually show you one that you might not know, except for maybe 1 or 2 people in the audience. You see who one of the people is. So it's a reduction from 3-dimensional matching. So there we are given a set system. So every set has size 3. Every vertex has one of 3 colors, and every set is multicolored. So it's just a 3-partite, 3-uniform hypergraph. And we want to count structures of this type, namely subsets of edges, n over 3 of them, so that any 2 of them are disjoint. So that we call the 3D matching. And I won't do this here, but it's a fact that the reduction from 3-set to 3-dimensional matching is actually parsimonious. If you just work out the reduction, it turns out to preserve the number of solutions exactly. So this means that we can start our reduction to the permanent from this problem. So the reduction, remember, it's an oracle reduction. So we want to compute the number of 3-dimensional matchings. And as an oracle, let's say we, as an intermediate step, we don't use the permanent, but we use size n matchings in a bipartite graph with n plus 3m vertices. So n is the number of elements, the number of vertices in the input, and m is the number of sets. And the way we do this is as follows. So we take any set, and we replace it with some gadget that is a bipartite graph. So for every set, we introduce 3 new vertices in this bipartite graph, and we connect them like that. So the 3 vertices are all connected to so it's a K32 with 2 of the vertices, but only 1 vertex here, 1 special color class, the first color class, is connected to the first edge there, to the first set vertex there. So that's the gadget, right? So in the bottom we will have n vertices, and up here we will have 3m vertices. Yeah. And then what does the set gadget do? Well, if the set is selected, we sort of want to So we sort of want to make sure that if the set is selected, then we know in how many ways there are matchings on this set gadget. Okay, so if it's selected, let's say we call it selected if the special color vertex is actually matched to a vertex in the set gadget. So in this case we have two matchings of this type. But then there are nasty cases where the set gadget is only partially matched. So some of them are left free, and we want to rule that out. Because this would mean that the sets in the input are not disjoint when we choose them. They're not a 3D matching. So whenever we have at least one edge to a set gadget, we want all of them to be there. Okay, let's just look at the case here where one of them is missing, namely this leading edge. So let's say this one is missing, then and all others are present, or two others are present. Then the total number of matchings is 6. Okay, and now those of you who have seen this type of argument before will see that, well, there's a difference between 2 and 6. Yeah. And in particular, if you count mod 3, this will zero out. This will be 0. And if you count mod 3, this will be 2. Yeah. So in particular, mod 3, we know now that every 3-dimensional matching leads to 2 size n matchings. Well, mod 3. Okay, so we can relate these two numbers. And yeah, it didn't show all of the cases, but this also works when only, let's say, this vertex is matched into the gadget, because then we have 3 cases, and their mod 3 are also cancel. So the trick now to get this reduction to work is to use higher moduli. So we can, this gadget works for higher moduli too. I mean, there are gadgets for higher moduli. And then use the Chinese remainder theorem. And if you do this, then you can recover the numbers exactly. Okay, so let me...
I mean that you are using a multiplication of distinct primes? What is this?
The moduli are all primes. Yeah.
Multiplication of primes, right? Like in the Chinese remainder theorem.
I don't understand your question. So if you, okay.
Chinese remainder theorem speaks about multiplication.
So if you know a number modulo, modulo 2, modulo 3, modulo 5, up to like log n many numbers, then you can recover the number. Okay, and now for the last step, we still need to reduce from this bipartite version, so k plus n bipartite graphs, and we count k matchings there. So these are maximal or maximum matchings in that graph. We need to reduce from that to the permanent, but that's fairly standard. So if we have a k plus n bipartite graph on the left, then we map it to an n plus n bipartite graph by just adding filler vertices and connecting them with everything. And then, so n minus k new vertices we will have. And then the number of perfect matchings in this new graph is n minus k factorial times the number of perfect matchings in the input graph. So this means that from the number here, we can recover the number on the left. Okay, so let me just summarize. We went from 3 CNF set with a parsimonious reduction. And we used the Chinese remainder theorem to get to 3-dimensional matching mod D or mod P. And we have a bunch of instances here. And then we use the simple gadget that I showed you to reduce from each of these problems, or from the mod p version of this problem, to the mod p version of k matchings in k plus n bipartite graphs. And then we use the simple standard reduction to go back to the permanent. Yeah, so this is a very non-obscure proof that the permanent is hard, or it should be. At least the gadgets, all of these gadgets are extremely simple. Whereas all reductions that I know that have been used before use these clause gadgets, and they use like this XOR gadget or something similar.
Sorry, when did it prove before?
It was proved before, of course, yeah.
But which year?
79
Old one.
by Valiant. Yeah, this is an old one. Okay, let me move on to fine-grained. Well, this is grain, and we're going to make it fine.
Flour.
And so let's look at counting satisfying assignments of CNF formulas. There is very recent work of Rines and his co-author that you can actually deterministically compute the number of satisfying assignments of a CNF formula in time that's faster than 2 to the n. I guess his contribution was to make this deterministic. So in particular, the savings, when f is a k-CNF formula, the savings are 1 over k, order 1 over k. And if f has c times n clauses, then the savings are 1 over log c. And this sort of matches the decision case where we can do this too, where we get similar kind of savings. And then sort of what we can do using, well, one hypothesis that we might have is that this is optimal, of course. So what is the hypothesis? Number ETH is just this hypothesis. It's just ETH lifted to a number set. The specification lemma works just as before. Also, it preserves the number of solutions. Yes?
Not our proof.
Not, well, almost. You just need to add some small variables that you set. So okay. So in your in the sunflower argument, either you pick the core or you don't pick it. And you don't pick it. If you don't pick it, you need to set the variables to 0. Then
It doesn't mess everything up.
It doesn't. No. Yeah, I checked this at some point. Yeah. It's also published. I just didn't want to put it there. Yeah. So the specification lemma. Oh, what is that even? Yeah, it means we can assume that m is order n, where the order only depends on k. And then, of course, we can formulate the strong ETH for this sort of thing. And this is a VK assumption. So if SETH is true, then number SETH is true. So it's the weakest assumption here would be number ETH. So let's look at the fine-grained complexity of the permanent. So just this year, Radu improved our hardness result for the permanent, and he showed that if the permanent can be computed in sub-exponential time, so little o of d in the exponent, then number ETH is false. So yeah, this work from before only could show that the randomized ETH is false under this assumption. Then I want to mention like work that's similar to like what happens when the density is bounded. So if the matrix has only few entries, only order n entries that are non-zero, then the permanent can actually be computed faster than 2 to the d. And that's similar to the SAT case. And this state of affairs may motivate some to define the PETH, or PETH, which is that the permanent cannot be computed in 1.999 to the n, or d rather. Unfortunately, I'm not aware of any results that start from here and reduce somewhere, but maybe some of you guys can correct me on that.
Is that implied by set?
No, so we don't know. We don't know the relationship between path and Seth. That's an open problem. Okay, and then I want to mention that this somewhat surprising fact that if you count solutions of two CNF formulas, you remain hard. In particular, and you remain number ETH hard. So what do you need to prove? Well, we need to reduce from counting satisfying assignments of 3 CNF formulas to the problem of finding satisfying assignments of 2 CNFs. And how do we do it? Well, we just use the falsification lemma first, which guarantees that every variable appears a constant number of times. Then we use this new proof that the permanent is hard, and some little extra trick to get to this problem, which is that counting the number of all matchings in the graph, not just perfect matchings, all matchings in the graph, even if it had constant degree, this is hard under strong ETH, under number strong ETH. And then from there we can get to this problem very, very easily, because just look at any vertex. It has constant degree. And now for every edge, we add a variable. And for every vertex, we add this set of constraints. Yeah, but we can't pick x at the same time as we pick y, because then it wouldn't be a matching. And we do this for all pairs of edges incident to any vertex. Okay, so and then this shows that number set for 2 CNFs is number SETH hard. So this is also a rather simple observation from here. So now let's look at some counting problems and on some progress or some results in the literature in counting problems. So we've seen counting perfect matchings in bipartite graphs, but what about general graphs? So in bipartite graphs, we have an n-half times n-half matrix, and then we count the perfect matchings in the bipartite graph with n-half plus n-half vertices. And that's how we introduce the permanent. And this leads to a 2 to the n-half algorithm using Reiser's formula. And then Andreas actually was able to get this type of running time even for general graphs. So we can count perfect matchings in general graphs in time 2 to the n-half, which is better than the obvious 2 to the n algorithm. I guess the obvious algorithm would be 2 to the m. So it's even much better than that. Okay, another problem would be Q colorings. So we could count all colorings, proper colorings of a certain graph with Q colors. So this problem leads to the following sort of interesting object, namely the chromatic polynomial. It's this function that maps a graph and a number q to the number of proper Q colorings of the graph. And I want to argue that this is a polynomial. It's very fast. If you haven't seen it, you will maybe enjoy this. So if we have a graph and there is an edge E, then we look at the deletion-contraction, the deletion of this edge E and the contraction of this edge E. So in the deletion, we delete the edge, and in the contraction, we merge the two incident vertices. And now it turns out that if we count if we want to count proper Q colorings here, then we might as well count all proper Q colorings here. But this doesn't quite work because we would also count those Q colorings where the two vertices get the same color. But we can just subtract the proper Q colorings of this contracted graph. And then we exactly get this relationship. The number of proper Q colorings of G is equal to that of G minus E and that of G contract E. That's, yeah. And then in the base case, we don't have any edges left. So we have K vertices. And then the number of Q colorings is just Q to the K. So using this argument, we can see that this object is actually a polynomial. By induction on, let's say, the size of the graph, we can see this. And it has degree n. Yes?
Looks like you're going to pick up parallel edges. Is there no deletion-contraction?
Well, since we're counting colorings, parallel edges don't matter. So we would just remove them. Okay, so this is a polynomial. And how fast can we compute this, or how fast can we compute Q colorings? The deletion-contraction algorithm, I mean, this formula gives an algorithm, a natural algorithm, that runs in time 2 to the m, which is already faster than the d to the, or might be faster than the q to the n. Yeah. That would be the naive approach. Okay, and I think Andreas mentioned yesterday that you can indeed compute this also in 2 to the n time. So you can replace the dependency on the number of edges with that of the number of vertices. And then under the ETH, we know that there is no 2 to the little o of n algorithm for Q coloring. I suppose that's just using the sparsification lemma and then following the standard reduction. And of course, we would like to lift this to number ETH, but I will mention this later. So let's first generalize the chromatic polynomial. So this will be this crazy polynomial. And I won't say much about it except that it generalizes the chromatic polynomial. Namely, if you plug in y equal to 0 here, then some instantiation of this gives the chromatic polynomial up to some factors that you can easily compute. And the Tutte polynomial has been heavily studied in counting complexity. And before that, even, it has been heavily studied by physicists because it tells them something about the Ising model and the Potts model. And they have long conjectured that this Tutte polynomial is hard to compute. And this has actually been proven then by the counting complexity community. And then apart from those, there are many other combinatorial problems. So the trivial algorithm to compute this runs in time 2 to the m, 2 to the number of edges, because the summation goes over all subsets of edges. And almost all people are in this room have proved that this can also be done in 2 to the n time. No, all of them are in the room, right? Oh, yeah. And on the complementary side, I guess, so in 1990 they did this. They showed that the Tutte polynomial is sharply hard. And then we sort of lifted it to the ETH world, and Radu, with this idea, made it into, proved that you cannot do it in 2 to the little o of m time under the number ETH. And I will say in a minute what the main proof idea is here. But what does it even mean? Yeah, we said that the Tutte polynomial generalizes the chromatic polynomial. So of course it sort of generalizes Q coloring, and we can't compute it in sub-exponential time. We already knew that. So what does this even mean here? So let me just mention the Tutte plane. So when you fix x and y, they are just constants now. And for this, or parameters for this computational problem, or constants. And the input is a graph G. And you want to compute T of G at this point xy. So then for every xy, you get a computational problem. And you can wonder how hard it is to compute that problem. And every point actually corresponds to some nice combinatorial object, and you cover many of them if you study sort of this, study it in this setting. So the results, or I think the most recent picture of what the Tutte plane looks like from a fine-grained perspective is this one. So for every xy, we have a computational problem. And if you happen to be outside of any of these lines, axes are okay, then your number ETH hard. And if you are on one of the green lines, then, or points, then you're poly-time. And the yellow line is open. So it's number P hard by this result from the 90s, but it's open under, this should say ETH. Under strong ETH, everything is open here. Yeah? Under ETH, it's open. And let me just say give you one case, one specific case where this is open. It's this point. So this gives you a computational problem, namely this one. So you're given a graph, and you want to count all forests, not just spanning forests, and you want to have, a forest with k edges should get weight 2 to the k. And we don't know whether this is hard under ETH. If you resolve it, then the Tutte plane there would be a complete dichotomy, which would be nice. Okay, so what is the method used here? So the method used is polynomial interpolation. In particular, we know in the Tutte plane, I said that if y is equal to 0, then we get the chromatic polynomial. So we already know that y equal to 0 is hard everywhere, except if you have one coloring and two coloring. These are these points. Yeah. So this whole line is hard already. Now we just need to sort of move off that line. And we do that using polynomial interpolation. So let's say we have a polynomial of degree d. And we can somehow generate d plus 1 samples, which means we can generate points where we evaluate the polynomial. And we can get access to the value. Then this is already enough to compute the polynomial. So we can compute all the coefficients of this polynomial in polynomial time. That's what we refer to as, or this is what interpolation means in this context. And interpolation has been used a lot in counting complexity. So for example, let's say the Tutte polynomial, just to give you something to think about, and let's say it only has one variable, so we specialize it to a particular line, or hyperbola actually. So it has degree m. And let's say we want to show that evaluating this polynomial at a certain point z is hard. So what this means is that we need to reduce to that computation problem from some hard problem. And let's say we know some point on this line, some point in this polynomial already is hard. So some point, let's say at 17, if we plug in 17, we get the number of 16 colorings or whatever. And that we already know to be hard. So we need to reduce from that point 17 to the point z to show that it's hard. Yeah?
Tg of 17 would be a polynomial.
Tg 17 would be a point. It would be a value. If we plug in some value here, no. So z, forget the x, y variables. You can be the only, you are the only person who can be confused about this. Yeah. No, just it has one variable. That's fine. Okay, so we need to reduce to that point. And of course, if we interpolate the whole polynomial, then we can also compute the hard point. So we just need to interpolate the polynomial. That's the task. So what we will need is we will need to come up with sample points C2, C3, C4, and so on, where we can also compute the polynomial. But of course we can't do that because the only oracle that we have is this one. So what do? Well, we modify the graph in some way so that the point moves. So in order to compute the polynomial at point zi, we actually move to a different graph, gi, which we plug into the polynomial, and there we look at the point z. Yeah, so the reduction is in the Tutte polynomial, it often looks like this, exactly like this. Every edge gets replaced by a path of length I. And that's called stretching. And when you do that, you sort of mess with the exponents of z in such a way that you move that point. So in order to interpolate on this line, what we need is m plus 1 samples, because m is the degree of the polynomial. And this also means that we need at least m plus 1 different gadgets if we use this approach, because we want to have different graphs here. But that means that the size of the gadget has to be at least logarithmic in the number of gadgets that we need. Or some gadget will have size logarithmic in m. Yeah, so the total number of edges here might get really large. So if we just do this path thing, then we might square the number of edges. Yeah, every edge gets replaced by a path of length m, then we would square the number of edges. But as a fine-grained reduction, this is not good enough. If we're clever, we could get this path, or the same functionality as the path in a log-size gadget, but even that wouldn't be enough. So this argument just says that we need a super constant size gadget here. And no matter what we do, like univariate interpolation will only rule out running times of this form, like 2 to the m over polylog m, under number ETH. So then Radu's idea is to not do univariate interpolation, but multivariate interpolation. So if we think, and now I sort of chose to write down the Tutte polynomial, or some version of it. If we think of this polynomial, let's say q is a constant. It's like 17. So it's the line that corresponds to 17 colorings. And then in Z, we have a univariate polynomial. So how do we get this to be a multivariate polynomial? Well, we partition the edges into n over r blocks, each of size r. And each block gets their own variable. So we don't just have one variable z for all edges, but we partition the edges, and then we distribute them accordingly to these new variables. So now we have a multivariate polynomial. And we have n over r of them. And the exponents here, they are just the intersection of the set A with the n over rth block, for example. So in particular, the exponents are all of size r at most, because every block has size r. And then we can use multivariate interpolation. And in order to do multivariate interpolation, we just need to evaluate the polynomial, or it's sufficient to evaluate this polynomial on a grid. So it's an r by r by r by r grid, where the number of dimensions is n over r. Yeah, so we need to be able to plug in r different values for all of the different variables and do this independently for all of them. Huh? So that's how we come up with or why r to the n over r samples are sufficient. And r to the n over r it's sub-exponential. Yeah, so that's sort of the crux here. We can do this. We invest a super polynomial but sub-exponential amount of time, but we can do this multivariate interpolation then in a better way. Why is this better? Well, we only need to plug in r different values for each variable. So this means for each edge is assigned, so an edge may be assigned to a specific variable, or is assigned to a specific variable, and this edge only needs to be replaced with r plus 1 distinct gadgets. It doesn't need to be log m different gadgets. And r is a constant, or we can choose it to be a constant. So we just need to find a constant number of different gadgets that sort of make this exponent do some predictable things in order to do this interpolation. Yeah, so this approach, this block interpolation approach, then is able to rule out 2 to the little o of m algorithms under number ETH. Okay. Any questions? And we move on. I will just mention a couple of things. Nothing technical anymore. So let's do approximate counting.
I didn't get the joke.
What? Pi mal Daumen.
Yeah, German joke.
What's the joke? I like joke.
It's a German idiom. Yes. Yes.
What is the approximate?
Oh, by the way, all artwork that I use is in the public domain, so no one can sue me. Huh?
I'm disappointed that you're using pi and not tau, but
yeah. Okay, let's do approximate counting. So the permanent, you can evaluate the permanent approximately if the entries are non-zero. If the entries are not negative. The entries of the matrix, then you can evaluate the permanent efficiently, meaning in time polynomial in n over epsilon, and you can approximate its value to a factor of 1 plus epsilon. So this was proved somewhat well in the 2000s. And much earlier, we actually knew that you can approximately count satisfying assignments to CNF formulas when you're given access to an NP oracle. Yeah, so if you Yeah, and the idea here is that you just query your oracle to begin with. Is there a solution? If there is, then you make it so that the number of solutions gets divided by half, and then you ask the oracle again. And how do you divide the number of solutions by half? You just intersect the solution space with a random hyperplane. That's sort of the basic idea of this approach. Yeah, and this classical result has been recently lifted to the fine-grained world, which I find very surprising. So in particular, if CNFS is in 1.999 to the n, so if strong ETH is false, then you can approximately count the number of satisfying assignments, also in sub-exponential time, slightly worse sub-exponential time. And you can do this to a very, to some factor of 1 plus epsilon, where epsilon is even sub-exponentially small. Of course, yeah, so this is in the same spirit as Stockmeyer. You assume something we sort of maybe don't believe, I don't know. Well, NP we believe, but strong ETH, maybe not. Yeah. So let me mention some more open problems. Namely, a lot of the counting complexity field tries to get dichotomy theorems for like classes of problems. I've shown you the spirit of one, like for the top polynomial. We have like a whole plane, and we can classify them into two cases. Either it's efficiently computable or hard. And in the same spirit, we can do this for lots of different problems. For constraint satisfaction problems, for example, we know that it's so the constraints here, the variables are not necessarily over a Boolean domain; they're over a finite domain. So so this theorem here says that whenever we know the set of allowed relations, then we can sort of determine efficiently whether the constraint satisfaction problem that allows these relations is in P, or whether it's number P complete. So Bulatov originally gave this with a non-computable sort of rule for whether it's in P or number P complete. And these guys made that distinction efficient. Or effective, rather. Yeah, and then you might ask, is there a dichotomy under number ETH? And the same, sort of the same type of question you can ask for weighted CSP, where every relation also gets a weight if it gets used. And you can also look at generalizations or related problems. You can look at whole end problems and ask there whether you get dichotomies under ETH. And this is my last slide before the summary slide. And I want to go back to the question why we even bother looking at counting. Well, if strong ETH is true, then yeah, this is going to be a bit gloomy. Then CNFS is in 2 to the n. Number CNFS is in 2 to the n. And QBFS is in 2 to the m. So they're all sort of equally bad. So it's not clear why it even makes a difference whether we look at number ETH or number strong ETH. But maybe my one remark here is that in practical applications, so if you actually want to, like in actual SAT solvers, CNFS is much easier than QBFS. So what might still be interesting is if there is a reduction from QBFS to counting satisfying assignments of CNF formulas. So this would be like a Toda type theorem in this world. And it would sort of show that counting is harder, at least as hard as a QBF. So that will be all. This is the summary. I put up some mostly open problems. Thanks.
So if we have the ETH only, so in the previous slide, do we have any implications?
No.
Nothing is implicated.
I mean, ETH implies number ETH, but we don't know anything. Yeah, we don't know that number ETH is harder than ETH. Like,
Any more questions?
yes.
In this result by Drexler that you mentioned on from CNF set to counting CNF set, is this like if there's a 1.98 algorithm, this algorithm also improves, or there's not like so there's a direct correlation between the running time for the algorithm for CNF set and the approximation factor and the running time you get for the counting problem?
As far as I'm able to parse the statement of his theorem, I would say yes. So if you have a 1.8 to the n algorithm for CNF set, then you get a 1.8 to 0001 algorithm for counting as well, for approximate counting. Any more questions?